Quick introduction about myself. I'm Vinay Sukumar. I lead the AI product team at Qualcomm. I always um, tell my family is my job is quite simple at Qualcomm, is to dream blue sky and then torture the engineering guys and my colleagues to translate that vision into reality, give or take, I would say. So today I wanted to kind of focus on what we are doing on the edge, specifically on the generative and agentic space. Qualcomm has a very big footprint on edge devices. We participate in a lot of consumer-based devices, be AR, VR, MR, and PCs, IoT devices, handhelds, and all kind of stuff. So that being said, at Qualcomm, every given year we launch, give or take, about 300 to 400 applications every year. So, and when you look at these applications, to a large extent, we can classify them as being historically very perception heavy. Perception here in this case, meaning looking at detection, classification, segmentation, enhancements, all to do with different modalities, either be vision, speech, text, even time series data. With time, I would say give or take about 3 or 4 years ago, after we had the DALI and the Chat GPT movement, there was a lot of, I would say, external demand to be in a position to express or drive a lot of generative or synthetic data creation on the edge. And we kind of, started to work with a lot of model builders. Could be Meta's team, or you could look at, the OpenAI team, a lot of these model creators to see if they could work with us to look at edge-based, models that we could go, infer. And this time we were able to accomplish that. I'll kind of walk you through some of the journey there. And this year we are starting to, commercialize a lot of agentic flows, especially for consumers and for enterprises. And moving forward, we're starting to look at participation in the physical AI space, where it's all about humanoids. What do we do from a mobility humanoid standpoint? What are some of the challenges there? Again, a broad spectrum, but today I'll kind of focus a little bit more on the generative and the agentic space. Now, as I mentioned before, working with a lot of clients of us, either be Microsoft, Google, Meta, BMW, GM, Cadillac, Amazon, quite a few folks of enterprise. We launch, plenty of generative AI use cases, and they're usually, not something secret out there. It's kind of classified into LLMs, multimodals, and vision models. In today's talk, I'll try to focus largely on the large language models, or the LLMs, and what are some of the use cases we have looked at, and what are some of the challenges that really, puts us into, how do we think differently, and what are some of the infrastructure needs that we need to focus specifically on the edge perspective. So first thing, what are some of the performance metrics? When you work with a lot of these, I would say white glove service providers, be the OEMs, what do they look for? And most of these guys are kind of anchored on four things. First thing is accuracy. What are some of the perplexity scores? What are the traditional benchmarks? Most of the use cases around productivity, around content creation, are you able to hit the benchmarks? Are you able to make it explainable? Are you able to make it repeatable? So those are some of the stuff that we anchor on. They have some very rigid accuracy metrics that we have to get done. Second one is all about speeds and feeds. It's inference performance. It's quality of service, latency. You measure at end-to-end latency or time to first token. That's an important metric. Then what will be the subsequent token generation speed? Now, it's just very much a bandwidth limited operation, but there's a lot of action and ask on increasing the amount of tokens that we can generate on the edge. Now, the third one is all about energy efficiency. When we started our journey on the edge on the generative AI space, it was mostly on demand, meaning that when you click a certain icon, click a certain app, that's when these large models get loaded from the flash to the RAM and you start looking at execution. But most of the use cases in the last 18 to 24 months has been mostly ubiquitous, meaning it's running on the background and then you take an instantaneous action based off a command from the user. So which means by definition, energy efficiency or tokens per joule becomes an extremely critical and important metric that we have to go emphasize and focus on and continue to look at making sure that the impact to battery life is as small as possible. And last but not the least, tokens per second per dollar is an important factor on the edge. Even though it's free of cost, it's all silicon on the edge. There is still a heavy amount of metrics on what is the cost model that is associated with that, and then how can you look at maintaining that over a period of time. So I'll touch on a few of these things, and hopefully, it's an useful information shared in today's talk. Now, I'll be the very first one to admit that when you look at edge-based AI inferencing, it's not easy. It is hard, in fact, very hard. And it's and there are many challenges associated with that. They're mostly around system challenges, meaning that what is the associated DRAM capacity that you have for these systems? What are some of the bandwidth associated? Most of these edge devices come with the flavors of LPDDR, either 4, 5, 5X, 5Z, and the associated number of channels limits the amount of bandwidth. And if you're going for a sustained use case, the energy consumption is extremely critical. And when you try to scale it across multiple swim lanes, you have to do a lot of customization on a per swim lane basis. So it's kind of challenging as you look at deploying it in a large scale environment. So in today's talk, what I'll do is I can only touch on a few because I'm pretty sure I can take half a day to walk through all of it and still won't be able to complete. So given I have about 10 minutes or so, I'll kind of latch on a few things that have seen a lot of interest. First one is all about the memory of the RAM footprint. Just to give you a perspective, most of these devices that we work on, if you look at phones as an example, they are between, I would say, give or take 12 to 16 gigabytes of RAM. The $1,000 mobile devices. When you look at PCs, all the Copilot Plus PCs, the minimum spec is about 16 gigabyte and go as much as 64 gigabytes. When you look at automotive environment, all the AI, the infotainment side of stuff, they go between 32 to 64 gigabytes. When you look at the other extreme, which is all about smart glasses, we recently launched the Android XR devices working with Samsung and Google. They are, give or take about 6 to 8 gigabytes of memory footprint. So you can see different form factors, different memory footprints. And we look at some of the popular models. In this case, I've kind of used a reference model of a 7 billion, large language model, quite popular. That is close to about 13 gigabytes of memory when you look at a floating point representation of that same model. That, by definition, is extremely difficult to look at phones, industrial IoT, AR, and VR kind of markets. It just doesn't work. So by definition, you have to look at how do I quantize it? And we look at elements of quantization is to really make sure you're able to get to that magic number of between 3 to 4 gigabytes, including your embedding tables, your context length, so that including your adapters to really make sure that you don't put a lot of stress and strain on the system memory. And because all of this is persistent, which means it's resident within the RAM and you don't have to keep transitioning from UFS or from flash into the RAM. And why is storing in the RAM important? Because it impacts your latency. So what we have done is, we have done a lot of work on quantization metrics. Obviously, well-known fact in the industry. The question has always been is, can I go from 16 bits to 8 bits to 4 bits to 2 bits? And how do I look at post-training quantization? How do I look at quantization of a training? How do I look at schemes of block quantization? How do I look at mixed precision to really drive towards reduced memory, faster inference, and also, have power efficiency gains for any sustained period of operations? So here we have an example. This is something that we are shipping today on all Microsoft Surface devices. We have worked with the Microsoft research team to actually do the Phi-Silica model. The Phi-Silica model, the large language model, is in this case on the left-hand side deployed on the neural processing unit on a 4-bit weight, 3.8 billion parameter is roughly about 2.5 gig out of the allocated 7 gig for us. On the right-hand side, we have gone towards the 2-bit representation is approximately 1.2 gig. At about 50%, wherein we looked at weights, and we made sure that it's just not purely reducing the precision of the weights. We had to do a lot of metrics on specialized training to get towards that point, because then you don't put a lot of stress on the RAM resources. Again, using the same concept, we expanded this into reasoning models. And this is the foundation for what we do on agent-based reasoning on the edge. So quite recently, in fact, it's going to be, I think, presented very soon to all the Copilot Plus users, wherein you have 14 billion parameter reasoning models all running on device, and using a 2-bit mode, you're able to get to a total memory consumption of about 7.8 gig, including supporting large context. So the possibility of doing large models, instruction-based, reasoning-based, is all fully doable if you look at some pretty good compression schemes, pretty good quantization schemes that we can get it done. And this was extremely important for us, because if you're not able to get this accomplished, then by definition, these large models cannot exist on device, and you're kind of forced towards operating between that 1 to 3 billion parameters, which is okay for some tasks, but when you go towards reasoning tasks, that just don't work. Second one is all about available bandwidth. As I mentioned before, most of the edge-based devices are based of LPDDR technology. I've kind of latched out, from 5x, 6, and the different frequency ranges that they operate. At best case scenario, we're getting, give or take today is about 80 to 90 gigabits per second. Moving forward, you're going to get, give or take, about 130 to 140 gigabits per second using a 4-channel peak DDR, assuming that all the lanes are fully utilized. And most of the use cases that most of these OEMs, most of the are, I would say the developer community is asking for is, towards 100 tokens per second for a 7 billion parameter model. With this bandwidth, you can only get to approximately 20, 30, maybe 35, 40 if you can push it. And that's just not going to be sufficient. And on top of it, as you go towards longer context length, all these numbers that I provided are give or take in the 4K to 8K context length. And now we're trying to push towards 64, 128, and much more higher as you go towards agentic flows. And that becomes an extremely big challenge that we are not able to accomplish it given the limitations in the bandwidth. And this is something that, what happens using the current Gemma 7B model. If you have the certain question beside the first law of robotics, because of the auto-regressive nature, this is how the token generation usually works. It's not bad. It's, it works, but it's not the speed that you're really looking for. So then we kind of move towards the elements of speculation. Now, they're obviously, well documented. There's a lot of speculation techniques, eaglets, Medusa, self-speculative decoding, all kind of elements. So we have done something very similar where we have taken, what you call the student teacher relationship models. We have built a lot of these draft models. These draft models are very much tied to a specific large model. And using the elements of speculation, you're able to increase the token rate. And in this specific instance, again, using the same prompt to recite the first law of robotics, you're able to get close to at least 2 to 2.5x increase in token rate. And this is quite helpful. Right now, we're getting more towards the traditional 20 to 30 is now pushing towards 40 to 60. And now, using continuous algorithm investigations, we're now trying to get towards 90 to 100. That's our goal for a 7 billion parameter model. We'll get there, but I'm just saying is these are, again, some of the constraints that get pushed on why we really have to go towards higher token and how we're able to accomplish that. Okay, the next one we'll go slightly differently. Is less about memory and token, and this is an important challenge as you're going towards, agentic flows. We at Qualcomm are totally pushing toward what we call as hybrid scenarios. And one such concept is how do you look at smart data capture and processing from the display or smart logging to really create a knowledge graph for the user, which means that can I take information from the screen, based off the permissions provided by the user, translating that into a certain embedding vectors that can be stored in the local database. And one of the biggest challenges is, if I have to create a knowledge graph, it needs to be running constantly. And by definition, if I am trying to run it quite constantly, it puts a lot of stress on our battery life. Our goal is, if I take a 3 billion multimodal to really look at information extraction, the impact is about, with less than 1% impact to the battery life, but we need to keep it much more smaller. So the challenge becomes is how do I make it a lot more intelligent to get things going? So what we have done is, the screenshots, the very first one, it's all about periodic, happens once every 10 seconds using speculation. What we have proposed is, and that we're kind of getting into system commercialization, is the bottom half is all about smart screen selection, which is going to be mostly activity driven and user preference driven, wherein you can take specific dynamic window extraction windows and push towards it. So end of the day, our goal is you are trying to target about less than 250 milliamps, if possible, if you can get to that, and then have less than um, I would say 600 to 700 shots that you can take at any given point of time. If you're able to accomplish that, that's I would say a North Star. We are there. We're not there yet, but that's what we kind of accomplishing. Okay, so I'm pretty much out of time. So I'll kind of summarize a few things. First one, as I mentioned, most of our inference AI applications are transitioning from perception to generative and agentic space. This has been quite popular for us. And for us, in about 30 to 40 use cases, almost, every 6 months we launch working with a lot of vendors. So, it's really, getting quite popular out there. And And also, this important thing is that the quality of the large models is getting better. You can see a lot of these SLMs now being trained specifically for certain tasks, for certain domains. We're able to take those models and get a lot of use cases developed on top of it. As I mentioned before, AI inferencing on the edge is quite hard. In fact, very hard. It's not something very easy, but we put a lot of engineering talent to really focus on these system challenges, especially on speculation, on bandwidth, or on memory compression techniques, or looking at smart logging, looking at vector database creation, so that we can look at these hybrid agentic flows. And yeah, so that was pretty much my last statement. As I mentioned, I was running a little bit out of time, could not talk through all of it, but I'll be available after the talk if there's any questions. And thank you all for the opportunity.